I'm Steve Burgess. I'm the president of Foresight Institute. Thank you. I understand you're a forgiving group because I'm going to ask forgiveness in advance. I'm going to give it around because I just finished my first half marathon last Saturday. And I've never given a BIL Talk, so I'm nervous. So, that's the same thing that's in front of me. That's great. Okay, so I want to talk a little about how nanotechnology, atomically precise manufacturing, and abundance kind of feed each other. In particular, how to create a different kind of abundance in the world than we currently have, or not that we don't have enough of. So, I've been doing digital forensics for decades. It's been my profession. And the thing I notice is that things I deal with are like documents, electronic documents that used to be pages, and photographs that used to be Polaroids, and videos that used to be film, and all this stuff now is zeros and ones. And it got me to thinking, of course, I've been involved with Foresight for quite a long time. How can we have digital control of physical matter? Is that a possibility? So I want you to go on a little mental visual exercise with me. How we get our stuff right now, our physical stuff. So first, we blow up a mountain. And we blow up all the animals and plants on top of that mountain. And we dig big holes in that mountain. We use enormous amounts of energy to pull the stuff out of that mountain. And then sometimes we leave behind pretty colors on that mountain that can be the result of minerals and acids being used to break the stuff down. But we're not done, because then we need to load all that stuff onto trucks and use a whole bunch more energy, and whatever it is, we're using energy and creating pollution to get that stuff to a place where we can process it, sometimes hundreds or thousands of miles away. And then we use copious other amounts of energy to melt that stuff down so we can turn it into things that we want to turn it into. And I'll skip the next few steps, which include rolling out the metal and stamping out the metal and turning it into other things and packaging it. And then it turns into something we want. So you get into your metal box and you burn a little more energy and create a little more pollution and go down to the store, maybe Uber down to the store, and they burn the energy for you. And we get the result, a fork. Yay! We blew up a mountain to get a fork. Or in this case, we dug up old dinosaurs and plants because there's a plastic fork. So, and we're not done. Because when we're done with the fork, we get to create some more havoc on the planet. And this might be in the form of just trash lying on the side of the road, in the form of, landfills, in the form of giant gyres of plastic in the North Pacific. So, why is it like this? It's like this because the way that we do economics. We do economics, it's kind of a zero-sum game. Just like it's kind of a negative-sum game with the planet, it's kind of a zero-sum game economically. Our economics is built around deciding who wins and who loses. Who gets more, who gets less. That's why it is the dismal science, if it is a science at all. Because you're there trying to find out who's going to lose the worst. So, there's not even, when it comes to abundance or lack of scarcity, there's not even a way to get scarcity out of the picture in the economic equation. You have to divide by zero, and as you can see, it doesn't work out well. So I tried to think of an image that was about abundance, and I started looking for a great picture of about abundance. And I saw people, raising their hands to the sun, jumping up and down a little bit, being showered with cash, cornucopias, and to me that seemed to be kind of a limiting idea of what abundance is. And I thought about, well, let's put up this image of the Mandelbrot set, first because it's completely cool, and second because it takes a simple equation and creates infinite complexity out of it. And so in a sense, it's the actual antithesis of scarcity. So I'm using this as my image for abundance. You don't have to. We're working our way away from using so much stuff to create the stuff we want. So for instance, this top image is a laser printer circa 1977. And, I'm not sure it would fit in my office at all. And we see in the little lower right-hand corner for about $100, a laser printer today that fits on the corner of your desk. Excuse me. And here we have publishing. In the upper left-hand corner, we have a newspaper machine, which I don't know when that's from, but I love the image. And the lower right-hand corner, what publishing is today. Desktop publishing, the thing that didn't exist when I started my business. Corner of a desk. Giant machine. I think I might blow that up and put it in my room. And now we have desktop manufacturing. This thing you get at, dare I say, at Walmart for $200, and you create useful things. It doesn't, create a podium or a speaker, at least not yet. Excuse me. But you can make useful things like things to repair your glasses or spare gears or toys to play with. So, but we need to get to the next step in a different way. We need to take kind of a quantum leap. And so, how do we get there? And we start talking about nanotechnology. And molecular manufacturing. Manufacturing things from the molecules up is a whole different way of doing things than manufacturing things from blowing out the mountaintops down. So let's define nanotechnology. A nanometer is a billionth of a meter, and nanotechnology is just nanometer scale technology. So the minimum length for nanotechnology is a nanometer, and the maximum length for the definition of it is generally accepted is 100 nanometers. So an area that would be between 1 and 10,000 square nanometers, or 100 times 100 is 10,000, or 1 to 1,000,000 cubic nanometers. So that's 100 by 100 by 100 is a million. But what does that look like? Well, DNA is 2.5 nanometers in size on average. Who here has DNA? And then about 1,000 times bigger than that is bacteria. And a large raindrop, a good-sized raindrop, is about 1,000 times bigger than that, or 2.5 millimeters. A single-walled carbon nanotube is about a nanometer across. 100,000 times bigger than that is a strand of hair, if you happen to be so lucky to have some. And a house is about 100,000 times that, which would be pretty spooky to walk into 10,000 strands, 100,000 strands of hair, but that's the scale of it. Your average nanoparticle is about 4 nanometers in size. An ant is 1,000,000 times bigger than that, at 4 millimeters. And the racetrack in Indianapolis, that's 1,000,000 times bigger than that. Around, it's about 4 kilometers per lap, during which they probably run over millions of ants. So, the thing is, when we're dealing with particles on that scale, we're dealing with a whole different way of manufacturing. Right now, we have to sort of break down these things into specialized materials. But if we're building things with materials that are common, abundant, like carbon and silicon, which are hyperabundant, a tree is a nanofactory. It turns air and water into wood. But we could hopefully do something like that with dirt, basically. So here's an early model of what a personal nanofactory might look like, something that might sit next to your microwave or in the study. It's simplified. It's showing a bunch of sugar cubes here. Not sugar cubes, but what they're supposed to be is constituent parts of a bigger machine. So it takes a lot of, because it operates at such a small scale, it would operate much faster. And you'd be able to basically have a slurry of materials coming in the back of it, like as a utility, that's basically enhanced dirt, enriched dirt, and coming into your house like electricity and water do now. And you to be manufacturing these things. We're not there yet, but it's something that we should be able to do. And also, by the way, hopefully you could throw your fork in the back of it and you can disassemble it. Personal nanofactory. So atoms are different than bits, because bits, digital data, it's just zeros and ones. Atoms are a little more complex. They have different kinds of rules. You can put any zero next to any other one, neither one minds. certain atoms don't like being next to other atoms. So you have to figure that stuff out, and it's a more complex thing. So we need more work. We have modeled many of these things, but we need a lot more work to actually make it happen. Atoms are harder than bits. That's all the same stuff I just said. But to get an idea of of the kind of scale of things, War and Peace is like what, a 5-pound book, right? And I don't know if you can see up here, but it's about a 1.5 megabyte file. And that little flash drive there holds 16 gigabytes, weighs a fraction of an ounce. You can fit 10,000 War and Pieces in that little thing. And we certainly had something like 10,000 wars. I assert that a lot of wars, and maybe the majority of wars, are fought over resources. And we're talking about making resources easier and more plentiful. Even the people who fight over religion and philosophy and just for power are empowered by their control over the resources. So we need to think about what abundance looks like. Here's my image for it, but I have 3 minutes and 33 seconds left, so you have to imagine for yourself. So what I want to do is talk a little bit more about what we need to do to get there from here. So one thing that we need is artificial intelligence. We need actually working artificial intelligence to help us figure this stuff out. These are hard problems. Help us figure out how to put the atoms together without them bouncing off. These are not easy problems. At the same time, artificial intelligence, in order to operate at the scale it needs to operate at, needs to be down in kind of the nanometer scale in order for those signals to go back and forth fast enough. So they need each other. We need atomically precise manufacturing. I stole this image from my friend Jay Storrs Hall book cover. I hope he doesn't mind. But anyway, we need that in order to be able to build these things, and that we've been talking about. We need open source. You know, in order for personal nanofactories to be manufacturing the stuff you need out of basically dirt, we need the designs for the AI to be able to help us build that stuff. So open source is real. You know, there'll still be a for-profit side, but if we can get the essentials covered by these personal nanofactories, or whatever they call them in Star Trek. What do they call them in Star Trek? Replicator. We need open source. And you know, the Gucci handbags you'll pay a licensing fee for, whereas the other kind of handbags, or the roof kits, like the IKEA personal nanofactory, so you can snap the things together. We need a new economics. I was just talking with one of the wranglers, I think, about her work on abundance, and we actually need a new kind of economics. There's an article I wrote on it a few years ago. You can see the link there. So, in order to step up to the plate, what do we need? We need us, all of you guys, or at least most of you guys, and me and so forth, to speak out for science. We need to fund basic research. We right now have an administration that has, I'm sure a few of you know, it's not really pro-science. We need to fund atomically precise manufacturing. The Department of Energy has some projects going. We don't want to see them lose that funding. We need to fund and help assist the advance of artificial intelligence, a lot of which is going on around here, fortunately. We need to promote open source and those kind of open source heroes to move beyond software into actually the digital control of physical matter. And somebody needs to write a text on economic abundance. We need to hear, maybe create a class or two on economic abundance. I'm no economist, I'm very much a generalist. And that's my email address if you want to get in touch with me. I have 30 seconds left.